Hello everyone, we are the Cardinal Castaways. We are representing Lamar University for the Alternate Treadmill for Explorations Missions Tsgc Design Challenge. Our outline for today's presentation consists of Tsgc design specifications, our design concept with our calculations and platform diagrams, also our element analysis and different types of exercises we accomplish with our design. This is our team members from left to right. We have Rich Healy, Dushara Sahan, Christian Chavez, Isaac Santillan, Edgardo Ramirez, and our team leader, James Furby.
Now for our design challenge and project background. The main focus of our project was to come up with an idea to mitigate the physiological effects that crew members in space experience during their exploration missions. So basically what we had to do was we had to come up with an alternate exercise equipment similar to the treadmill. The reasoning behind that was that the original treadmill is too heavy and too big. So we had to design something similar that had the same benefits as a treadmill. Now for the Tsgc Design Challenge specifications. We had to make sure that the crew members were getting the appropriate impact and functionality of the exercise as well. Some of these things are the impact of the foot, just like whenever you're running or jumping, that vibration sensation that goes through your spinal cord and so forth. So we needed to basically simulate gravity in space, although we did have some constraints and factors to consider. Some of these constraints and factors were basically it can't be too big, you got to keep the mass under 100 pounds, making sure the volume of the equipment wasn't too big, and also being aware of the physical benefits of the treadmill and how it was going to be applied onto our new concept. For the areas of concern to take note of was making sure that the astronauts were getting the necessary exercise. This was very important because one has to consider an environment in microgravity. When the human body is out in microgravity, it tends to lose bone and muscle mass. That's because of the change of cardiac performance, which are some of the more detrimental effects of being out in space. As you can see from these charts, the aerial bone mass density percentage changes while in space.
In our initial concept for the exercise platform, we envisioned the user would move left to right over approximately 3 feet to allow some movement and associated required impact during exercise. Pulleys were to be fixed on the ends of the equipment. The platform is continuous, as will be seen in the mock-up photos later. The 3 blue lines are just 1 foot superimposed segments. In the center position, the lateral forces of the elastic are balanced. When the user is in the extreme left position, our calculations showed that lateral forces would be excessive due to the extreme angle of the more distant pulley. In a later iteration of the concept, shown at the bottom, the team decided to use moving pulleys that would move with the user. This, plus putting the track on an angle, served to reduce the severity of the angle, thereby reducing the calculated side load of the user to an acceptable level. Here we see the internal movement of the proposed movement system. Note that with the operator in an extreme left or right position, the opposite pulley is closer to the user and in a lower position, which reduces the angle of the elastic to the operator. This movement mitigates the lateral side pull experienced by the user. The frame for the platform is proposed to be built from titanium. Titanium was chosen for its desirable weight and strength properties. The model calculated weight is 66 pounds and appears to perform well in the FEA for the frame. This weight easily falls within the design requirements. The frame skeleton was modeled as 1-inch square tubing with 0.15-inch thick side panels and 0.2-inch thick top panels.
For the finite element analysis, we chose to do a 400-pound impact on a location that we perceive to be one of the weakest on the platform. The structure, being of skeletal tubing, has several overhanging locations. These locations are the weak points of the surface. The surface is made up of 8 equal squares with overhangs in the center of each. We chose to use a single square to impact with the entire force, representing a bad case scenario for the structure. The location chosen is denoted by the red circle in the displacement analysis. During the impact, The surface of the platform only experienced a 0.04 millimeter of displacement, proving that the design is incredibly sturdy and capable of supporting intensive exercising.
For the construction of our prototype, we were able to imitate our design using lumber rather than the preferred materials such as aluminum or titanium. As you can see from the pictures, the model came out to look pleasant and properly functioning.
The three photos shown represent the three extreme positions a user can take on the platform: the center, the left, and the right. While in the center, the user would experience the desired force of gravity and no lateral forces. This is because of the angles of the cables canceling each other out, as shown. But as you can see, due to the changing angles as the user moves to the far left or to the far right of the platform, they will experience some lateral forces, though these forces have been decreased significantly due to the pulley system. The renderings below show the position of the pulleys themselves as the user takes the various positions. Here we explain the difference in lateral and vertical forces between our pulley system and one that would have the pulley locked onto the sides of the platform. As you can see, both systems would experience relatively the same vertical force regardless of the user's position on the platform. The main issue comes with the lateral forces. While both systems would experience no lateral forces in the center, as the user moves to the edge of the platform, both systems would significantly increase. But by having the pulleys move with the user and decreasing the overall angle between the user and the platform, we've managed to significantly reduce the rise in lateral forces on both far ends of the platform from 66 pounds down to 26. This makes the platform much more stable and usable for safe exercise. Here we show the calculations for the simple example of the user on our platform moving from the center position to the far left position. Position 1 starts with the user having a 200-pound y-axis force representing gravity and a 0-pound x-axis force. As the user moves to position 2, the y-axis force will increase to 223 pounds, which is still very usable. The x-axis force, however, will increase to 26 pounds. And while this is a significant reduction from 66 pounds, 26 pounds is still a lot to have on the side while exercising. But modifications to the waist width and the angle difference can reduce that 26 pounds significantly.
Here are a few exercises that can be done in a 2x3 foot space using the lateral movement platform. You can do jumping jacks, squat jumps, side to side jumps, even mimic jump roping. And with a platform that has multiple activity gains, you can do yoga, boxing in place, and even do dance dance revolution.
Upon the completion of the prototype, the team was finally able to transform their design concept from a visualization into a reality. After a few test runs, numerous benefits were concluded in which will apply to not only the user, but NASA as well. As seen from the prototype construction, a main benefit is the simplicity of this design. This will lead to easy maintenance as the number of tools used will be kept at a minimum. Furthermore, considerable benefits are having the ability to retain spare weight for strength reinforcement, having the option to store items due to the platform being hollow, and maintaining the usage of power at an absolute zero. In conclusion, the team was capable of designing and constructing a prototype for the duration of the fall and spring semesters to which checked off each specification initially given by Tsgc. The Cardinal Castaways would like to greatly thank Lamar University professors, Dr. Zhao and the late Dr. Ong, for providing assistance to our team when needed. We are also thankful for our mentor, Philip Callan and his associates in regards to steering our design onto the right direction. Most importantly, we are grateful to be given such an opportunity to develop and present an idea with the potential of it being used on future space explorations. To Tsgc, the Design Challenge teams, and the viewers on YouTube, thank you all for listening.